This lesson forms the beginning of the unit on linear equations, and we're going to start with the simplest method of solving a system of linear equations, which is to do so graphically, or to draw the graphs of the different linear relations. So first of all, you should have enough of a background to remember that the graph of a linear relation forms a straight line. If you create a table of values, or if you use properties such as the slope and the y-intercept, you end up forming a straight line for each linear relation. In this unit, systems of linear equations, we're going to be looking at multiple linear relations. Usually we're going to be looking at two linear relations, or just a pair, but sometimes we can be looking at more than two for more complex problems. So if we graph two or more linear relations on the same set of axes, that has formed what's known as a linear system. To try to find the solution to a linear system, we are looking for the point where those lines intersect each other. And you can see I've just drawn a very simple sketch here at the bottom to illustrate that. In the blue, I have line A. In the red, I have line B. And the point where they cross, they only cross at one point, and so that point is going to have an x-coordinate and a y-coordinate based on, so that's going to be its x value, and that's going to be its y value. So this point of intersection is going to have an x and a y, and that is our solution to this system of linear equations. So let's dive right in, looking at some examples, keeping in mind that we are going to be drawing upon our skills when it comes to graphing linear relations. So you need to be able to do this quickly and easily. So here's my first system. Two very simple linear relations. Y equals negative x plus 4. Y is equal to x minus 2. So let's go ahead and start with that first one. So I'm going to do that first one in blue. Equation number 1. So what's the first piece of information I'm going to get out of equation number 1? It has a y-intercept. Maybe I'll just write this down here again. Y equals negative x plus 4. I'm going to use this piece of information. That is the y-intercept. And in front of the x, we remember that that's a number 1. And so that tells us that this has a slope equal to negative 1. And when we're graphing slope, sometimes we like to think of slope as rise over run. And so that's the same as negative 1 over 1. So let's graph this. The y-intercept is 4, so I find 4 on my coordinate grid, and I put a point there. Now I use the rise over run to form a step pattern. So this 1 on the bottom is a step to the right, and a negative 1 is a step down. So I take a step to the right by 1, and I take a step down by 1, and I end up with a point here. And I take a step to the right by 1 and down by 1, and I get another point. Right by 1, down by 1, and another point, and so on. And so I've got this. I'm just going to take out these arrows. I don't think they add much here. So I've got these points that line up. So I'll put on an actual line now. And I will extend that line. And then now I really should also put arrows on the end of my line to indicate that it keeps going indefinitely. Let's do the second equation. We have y equals x minus 2. So once again, I'm going to make use of the fact that this value, negative 2, is the y-intercept. And the number in front of the x here is, once again, it's a 1. And so that means that my slope is equal to 1 over 1, or just simply 1. But again, because I'm using that idea of a ladder or a step pattern, that 1 over 1 is going to be helpful. Switch back to red. So this means I'm going to go to the right by 1, but this time the numerator is positive, so that means I'm actually going to be going up each time I take a step to the right. So I take a step to the right by 1 and I go up by 1. Step to the right by 1, up by 1. Step to the right by 1, up by 1. Step to the right by 1, up by 1. And you can see, even just from drawing the points here, I didn't actually need to draw the lines in, because the points on their own have actually shown me where the intersection is between these two lines. But if you were being asked to do this as a question, you do need to complete the question. Once again, I'll indicate that these lines continue. And obviously, my point of intersection is right there. Sometimes instead of writing out point of intersection, we'll just use POI to represent point of intersection. Or you could just go ahead and write the coordinates. What's the x coordinate of this point? It's 3. And what is the y coordinate of this point? It's 1. Okay? So they're solving a fairly simple system graphically. Let's take a look at another system now. Sorry, this is just I use some software to produce the solution to this, so you can see a very nice graph of the same thing. But you can see there the point is very obviously 3, 1 where they cross. Okay, another system. So I'm not going to go through all the details about how to graph each of these by hand. I'm going to assume that you can do that, or that you can look it up. So all I'm going to do is I'm going to label this as system number 1, which I'm going to do in blue, or sorry, equation number 1, which I'll do in blue. It has a y-intercept of 4, and it has a slope of 2. Slope of 2 means I go to the right by 1 and up by 2. So there's another point. Now, if I kept going that way, I would end up going off of my graph to the right by 1 and try to go up by 2. Well, I can't really do that next point because I've lost the scale of my graph. To the right by 1 and up by 2 is the same as going to the left by 1 and down by 2. So I can continue my graph in either direction using the slope. Left by 1, down by 2. Left by 1, down by 2. Left by 1, down by 2. You just need to do enough of these so that you can see that this is very obviously, I've got a good straight line there. For the second equation, I have, now don't get thrown off by this second equation, y equals 2 minus x. That's in the form y equals mx plus b, it's just been rearranged. So we could rewrite this as, instead of, we normally like to have the x first, so negative x will go first, and although we don't write it, this is obviously a positive 2, so that's going to become negative x plus 2. So if you like to put it in a more familiar form, you can do that. This one has a y-intercept of 2. And this one has a slope of negative 1. That means to the right by 1 and down by 1. To the right by 1 and down by 1. Now obviously I'm moving away from where they're going to intersect, so now I'm going to go the other way. To the left by 1, the opposite. Right by 1, down by 1. Left by 1, up by 1. Left by 1, up by 1. And I can now connect to my dots to form my straight line. We take a look at our point of intersection, which is here. Well, what is that as a solution? Actually, That's kind of obscured some things, so I'm just going to. So here's my point of intersection. It's that dot. What are the coordinates of that dot? Well, can I actually read the y value here? Can I read an x value down here? Not really. This point is what we would say it's not a good point in the sense that it doesn't lie on any exact values on the grid. So we could estimate this. This looks like, well, it's between 2 and 3. It's a little bit past halfway. So maybe this y value is equal to 2 and 2/3. And that is the same as 8/3. And down here, well, I've kind of drawn this a little crookedly. It's between 0 and -1, but it's past halfway. And now, part of the reason I probably cheated a little bit here, I know that this is actually the correct answer, 8/3, but even looking at the graph, that's really a guess on my part. I don't know that that's the actual case. I am making an educated guess that that is 8/3. And the same thing is true here. I would have to make a guess as to what that is. So if you're trying to solve a linear system graphically, be aware that sometimes the answers are not going to be nice. They're not going to work out exactly. And you may have to estimate your answer. And that's one of the reasons why we learn to do this algebraically, which we'll look at in another lesson. So for now, we do our best guess. And so for this, for my best guess for x is I'm going to say x is -2/3. So my solution, I'm going to say, is -2/3, 8/3. And because I have the benefit of doing this with technology, I go to the next page and I actually have, actually that's not correctly written, that should say a -2/3 and 8/3. So we're not always going to get nice solutions to these things, and you need to keep that in mind. Sometimes it can be difficult. You can make a guess and you might get it right, or it can just be so impractical you're not going to be able to solve it graphically. So that's definitely a limitation of graphical solutions. They're easy most of the time, but they don't always get us what we're looking for. Okay, another one. Y equals x minus 3. We have an intercept at -3. The y-intercept is at -3. And now my slope is 1. So to the right by 1, up by 1. To the right by 1, up by 1. To the right by 1, up by 1. And I'm going to continue that trend. This one, well, this one is this second equation. Equation number 2. It's not written in the form y equals mx plus b. So we could change to y equals mx plus b. Or we could solve for the x-intercept and the y-intercept. And I'm going to do this one, not because it's better or worse, just because it's different. All the other ones we've looked at so far have been in the form y equals mx plus b. So for my x-intercept, I set y equal to 0. So when I set y equal to 0 in this equation, this -4y is going to become 0. And so I'm just going to be left with 4x equals 12. Divide both sides by 4, and I end up with x equals 3. For my y-intercept, I'm going to set x equal to 0. And when I do that, that means this 4x becomes 0, and I just end up with -4y equals 12. Divide both sides by -4, and I end up with y equals -3. I need to go back and actually put my line in for the blue one. And now let's go ahead and plot that x and y intercept. x equals 3 is right here. And if you did this blindly, you might say, I don't need to do any more. I found it. There's my point of intersection. But what is this y-intercept? It's at y equals -3. And I only need 2 points in order to draw my straight line. And you can probably see what's happening here. To join those 2 points together, I'm going to use a really thick line to show you that right over top of the first line that I drew, there is a second line. So what can we say about that's a pretty awful line. Do I have a better option? Let's go back. That's a little bit better. So what can we say about points of intersection? Well, we have a point of intersection here. We have a point of intersection here. But we also have a point of intersection here. The lines touch the same point here, and as a matter of fact, they touch the same points everywhere on the lines. So that means we actually have an infinite number of solutions. I might as well not have written that out. It's so bad looking. And a nicer graph on the next page. The way I've shown it here is in the red I've got y equals x minus 3. And in the blue I've got 4x minus 4y equals 12. And if I take those two, you can see that I can line them up and they turn out to be the exact same graph. Same idea, they overlap completely. So infinite solutions there. And finally, y equals 2x plus 4 and y equals 2x. So let's go ahead and graph those. So this is number 1. 2x plus 4 has a y-intercept of positive 4. The slope is 2. That means go over 1 and up 2. We've run out of room to go to the right, so now I have to go to the left. That means go to the left by 1 and go down by 2. Left by 1, down by 2. For the second equation, y equals 2x, that means that's the same as 2x plus 0. It has a y-intercept at 0, and it has a slope of 2. Over to the right by 1, up by 2. To the right by 1, up by 2. To the right by 1, up by 2. For the going the other direction, we go left by 1 and down by 2. Left by 1, down by 2. Left by 1, down by 2. And what do you notice about these two lines? These two lines are what we call parallel lines. They are never going to touch each other. And if we have lines that will never touch each other, the solution to this system is where they cross. So two parallel lines will never touch, so that means we will have no solution. So we've actually gone through a number of possibilities. There's the nice computer-generated version of the same thing. Quite obviously, they are parallel there. So we've gone through some different cases here. We have no solution. If the slopes are the same, but the intercepts are different, that's going to result in two parallel lines. And so we end up with no solution. When we have one solution, that's when we get a point of intersection. Most of the times that you do this, that's what you're going to get. And that's really going to be a useful result, a single point. What you have here is when you have different slopes, you get a point of intersection. So anytime you can write it, if you can write it in the form y equals mx plus b, As soon as you see that these slopes are different, you know you have a single point of intersection. The downside to this one is going to be that you're not always going to get really nice solutions. And that's a problem with graphical solutions in general. Yes, most often they will be nice, but sometimes they won't be. So you can't always resort to a graphical system unless you're okay getting an estimate for your solution. And then we can have infinitely many solutions. That occurs when we have the same slope and the same y-intercept, which really means we have the same line. You may have it represented differently. I'm just going to go back to the example we had for that one. It's a little cleaner here. So for this one, these two equations look different, but when you graph them, you end up with the same straight line. Okay, so you graph these, you end up with the same straight line. That's because this equation was actually the same. We could have rearranged this equation and we could have gotten the exact same thing out of it. Okay, so there's an introduction to solving systems of linear equations graphically.